Synchronous sequential circuits has certain timing specifications. So the timing specifications determine the maximum frequency at which the system can operate under. So in this video, our ultimate goal is to figure out what is the maximum frequency that a system can actually operate on. But before we actually do these calculations, I want to introduce a little bit about the timing specifications of general synchronous sequential systems. So in here, if you guys remember, we have a flip-flop. It doesn't have, so timing specification applies to flip-flops, registers, because remember, registers can be formed out of flip-flops. And generally speaking, what we have is we have an active edge that the flip-flop operates on. And for the sake of this, video, we're going to assume that the positive edge, which actually is the edge that's going from 0 to 1, is the edge that we care about in terms of the active edge of the registers or D flip-flops. So what the timing specification tells me is the following: is not everything actually appears exactly at the clock, okay? So there are some delays and some things and some timing specifications we have to follow. Specifically, what I have is I have inputs and I have outputs in here. And as it turns out to be that an input, in order for the flip-flop or the register to actually sample that input correctly, that input has to be kept for a certain period of time, and that period of time is what we call setup time. So for the setup time, you need to actually, for the setup time, you need to keep the input stable. So you shouldn't change the zeros to 1 around this time. And this is right before the clock, and we call it the setup time. And also, you should keep it you should keep that input at the same location or at the same state, basically 1s or 0, for a certain time after the active edge of the clock, which in this case it's the positive edge, and this time is what we call the hold time. So this window in here from the beginning to the end is what we call the aperture window, okay? And within the aperture window, I want the input to be stable. So if you wanna put a 0 at the input of this flip-flop, you should actually keep it stable for the before the clock and after the clock for a setup time and a hold time, basically within the whole aperture. If things happen, if things happen and you change that value, you're gonna get a metastability. Okay, so then what happens? Well, if you kept it stable, then this particular flip-flop it's going to sample whatever is on its input, which is D. And also this applies to registers. So it will sample whatever is on its D. However, the output will not be updated directly or instantaneously. It will take some time for the output to get updated. And that time is here, okay? And this is what we call the clock to Q. So generally speaking, you're going to see something we call it clock, okay, to Q, which is basically from the active edge of the clock to the output, which is Q. So in here you see a couple of actually clock to Qs. There's one that what we call the TCCQ, which is the contamination clock to Q. That's this one in here. So the contamination is actually, so this is how the output is. Again, it doesn't get updated automatically. This is where the active edge, it takes it some time to get updated. So the least amount of time it takes, or basically the fastest time, which is the shortest delay that it can take for that output to get updated, is what we call a contamination. Okay, so for the contamination delay or contamination clock to Q, that's the fastest that the output can change. However, the flip-flops usually have a range for the clock to Q. The contamination is the fastest, and what we call in here, which is the propagation delay, which is this one here, propagation clock to Q. So at the latest, basically, at this point, definitely the output will be changed. Of course, if the timing specification were followed, the constraints, the setup and the hold. Basically, if we kept this particular state here at 0 and 1, it will actually, at the propagation time, like the propagation time or afterwards, it will actually be stabilized or it will be sampled correctly. All right, so the key takeaways from here is I have a setup time, I have hold time, I have contamination to clock to Q, and I have propagation clock to Q. All right. So these time, setup time, and the hold time, the contamination, and the propagation clock to Q will help me figure out the maximum frequency that this system can operate at. And of course, the faster the frequency or the more the frequency, the more things you can do with the digital system. Well, all things considered, like there's other things to consider, but it's one of the things that we can actually increase the speed of the system. It's not necessarily the only thing, but it's one of the things that we can do. All right, so what I want to do is, before I actually get started, I want to talk a little bit about metastability. So I mentioned briefly that if you have violated the aperture and for some reason or another you actually changed it, you're going to get metastability. So let me show you what a metastability is. So what not metastability is the following. I'm going to have a D, and that D, this is my aperture window here. This is my active edge of the clock. I have to keep it within the setup, and I should keep it within the whole time. So for case 1, D is set at 1, and it didn't change within the aperture, so that's fine. You're going to see that the Q is going to 1. All right, for the case 2, you're going to see that D is set to 0, and it didn't change within the aperture, so you're going to see that the output will be set to 0. It will be sampled. The input will be sampled, and it will be stored within that flip-flop. Now, metastability happens if within the aperture window something happened, like it moved from 0 to 1. Okay, so as it turns out to be, that this causes metastability. So what is metastability? So I'm going to show you here, this is what metastability is, okay? So this is our active edge, and let's assume, well, the graph I'm showing you here, the active edge is actually the negative edge in here. That's fine. And the negative edge is basically the active edge. And what happened is, for some reason or another, apparently the input, which is in case 3, changed. So you're going to take a look at the output, and what you're going to see is something in here. So something in here, it's actually not 0 and not 1. This is my 1 and this is my 0. It's actually right in the middle in between. It's actually in the forbidden region. Remember, 1 could be 5 volts, for example, or 3.3 volts, depending on the technology you're using, or maybe even less nowadays. But it is within the forbidden range, and you should not have anything. It's not 0 and it's not 1. So metastability, it's this violating this aperture rule is actually going to call metastability, which means that the system is going to give you something unknown. It's actually not a state you want. It's not a 0, not a 1. However, this metastability eventually will stabilize and it will go away. And after a certain time, you're gonna get that thing to disappear. And however, one thing to think about, this is what we call a resolution time. Okay, so after a certain time, what we call a resolution time, you're gonna see that the metastability is gonna basically stabilize. The system is gonna stabilize. The amount of time it takes is actually unknown and unbounded. So it might take a long time or a very short time. We don't know. And this is actually bad. In a synchronous system, it's bad. You need to know everything about time. Okay, and the other bad thing is you don't know what it would resolute to. It could actually go to 1 or it could go to 0. So in this system, what I'm showing you is actually several attempts, several metastabilities just superimposed on each other. You can see that some of them actually go to 1, some of them go to 0. The system is the same. So two things is about metastability. I don't know the time it will take for it to actually stabilize, and I don't know what will it stabilize to, what value will it take eventually. Okay. All right, so to avoid metastability, we need to actually do some analysis on the system, figure out what the maximum frequency is, and whatnot. So what we're going to be doing is we're going to do some analysis, and the analysis is going to be performed in this very, very generic system. So this generic system, I do have some sort of a register here or flip-flop. You can think about it this way. It doesn't matter. It's the same. And I have another register here, R2. Okay, and in between them, I have a combinational circuit. That's CL for combinational logic. Okay, so what we're going to be doing is we're going to focus on R2 for most of the part. Okay, in terms of its timing constraint, we're going to figure out how we can actually satisfy the timing constraint for this R2. So the output coming from R1 is called Q1. It's going through some sort of a combinational circuit. It goes all the way through. It outputs D2, which is actually the input to the R2 that we care about. Okay, and that's what you see here on the timing diagram. So on the timing diagram, you get to see that this is the clock, and then of course I have some sort of a contamination clock to Q for Q1. Basically, it takes some time for Q1 to actually go, and contamination is the best. Basically, it's the fastest. Okay, and then through the combinational, as it turns out that even the combination has contamination and propagation. So the fastest time is this here. So from clock to D2, so basically from the clock edge, from the positive edge all the way to D2, it will take this time, it will take this time, and that's the best case scenario. This is the fastest, and this is what we call the contamination today. Okay. Similarly, you can see that on the other side, it might actually take the longest to actually get basically the propagation of R1 and the propagation of the combinational circuit. So what I'm trying to tell you is even the combinational circuit has basically the best case scenario and the worst case scenario. Okay, and I'm going to show you an example shortly to show you like how the contamination and the propagation are different. But for now, you should know that contamination is the fastest, propagation is the slowest. So we're going to be doing some analysis on here. So let's get started. So we're going to start with the setup time constraint, okay? So with the setup time constraint, again, the setup time tells me that before the active edge of the clock, which is around here before the active edge of the clock, what you need to do is the input to R2, we're going to focus on R2 for now, which is D2, have to be stable. So you should not change it within that here. So this is a setup time constraint. Okay, so let's figure out what does this graph is telling me. Well, this graph, our ultimate goal again is to figure out what's that TC is, which is basically the clock period. You can basically clock frequency or clock period is the same thing. Okay, and this tells me, okay, at the active edge of the clock, what happens is this particular flip-flop or register will take it some time, and that sometime I'm just going to consider the propagation delay, the fastest delay. Okay, that's the fastest one, not the fastest, the slowest delay actually. Okay, the propagation delay. So it'll take T P C to Q, so T propagation clock to Q. Okay, all right, and of course that signal is going to go through the combinational circuit here. So it will also, I'm just going to consider the worst case scenario, and that worst case scenario is propagation delay. So this is just the propagation delay of the combinational. And of course I want my system basically to be held for the setup time. So if you take a look at here, you can see that I'm only allowing that D2 here to change only around here. That's the only time while it's allowed to change, and that's about it. Okay, it should not change in here, and it cannot change in here. Well, it could change in here, but I'm just considering the worst case scenario. It could change in here a little bit. Maybe we get the contamination here and the contamination, but we're just gonna look at the worst case scenario. So what this tells me is, if you take a look at it, this is actually the worst case scenario. I cannot get anything any shorter anymore. So that tells me that T of C should be greater than or equal to, okay, so the period should be greater than or equal to the sum of all these signals in here, or the times. Okay, PCQ plus TPD plus T setup. Okay, all right, this is what I'm looking for actually. I'm looking for basically the TCQ. So now I have some sort of an equation to do, to actually plug in some numbers and figure them out. So the T setup is actually from the flip-flop. Okay, so it's part of the flip-flop. So the manufacturer of the flip-flop usually specify it. The TPCQ, which is propagation clock to Q, it's also from the flip-flop. So the same manufacturer decide this. Maybe not the manufacturer, maybe you decided to use certain register that has certain specification. So generally speaking, you don't have control over it. So what you have control over is then this here and maybe here. So if you do have control over the period that you can operate on, you can do this. But generally speaking, again, you get a customer or maybe a manager that tells you, hey, I want to operate at this particular clock speed, and you have to satisfy it. So you're only left with a TPD. Where is TPD, which is the T propagation delay. That's the propagation delay of the combinational circuit in here. So the only control you have here is actually how slow, or what's the slowest I can get from here to here, from the input to the output of the combinational logic. You might have to change your combinational logic design to satisfy that. And sometimes you're going to see that some people actually rearrange this equation. These are just written again just cleanly. You rearrange this equation and it tells you, well, in order for you to do this, you can actually constrain or construct a combinational circuit that has basically a propagation delay that is less than this particular value in here. Again, this value here is usually specified by the flip-flop. This one here is probably imposed to you on by a manager or customer or something like that, because you have it. So for example, in our FPGA board, we have 100 megahertz, maybe, which is 10 nanosecond in TFC. Okay, maybe that's it. We don't want to do any processing on that clock. I just want to use the native clock that comes on the board. So what's left for you is actually to change your combinational logic. All right, so now we move to hold time constraint. So in this figure, you're going to see that I'm only showing contamination delays, which are basically the shortest delay, which is the fastest responses that you can get. And again, in hold time, what we need to do is we need to make sure that D2, which is right here, okay, D2 is not changing, okay, within the T hold. So it has to be held after the active edge, okay? So it has to be held after the active edge, and you can see it's not changing in here. You can change it right after. Okay, so when can it change? Well, it can change after the contamination clock to Q and after the propagation clock to Q, which is here, so this one in here. So what this tells me, it tells me the following. It tells me the equation that T hold, okay, has to be less than TCD plus TCCQ, okay? All right, so of course you can do a little bit of algebra and move it around, and what you're going to get is again, you can do the TCD. So why did I do the TCD? For the same exact reason we mentioned before. Generally speaking, the T-hold and the TCCQ are actually part of the flip-flop specification. You don't have any control over it. And one another comment in here that you get to see is that TC, which is actually the clock period that we're actually after, does not appear in this equation. So as it turns out, the thing that satisfies the maximum frequency is actually the setup time, not the hold time. However, you should be careful that the hold time constraint is not actually violated. So you need to actually figure out that this inequality is correct, whether this one or this one is the same. Okay. So setup time and hold time. In summary, you're going to see that setup time is telling me that the combinational logic has to be fast, and the hold time is telling me it shouldn't be too fast. Okay, so you have to have that range. It's a very specific range. However, generally speaking, the TCCQ and the T-hold are set up in such a way that the hold time is very difficult to actually, very difficult to violate.